In the late 1950s, Soviet military planners ran the numbers on tactical nuclear warfare. The conclusion was uncomfortable. At detonation ranges where armor was expected to operate, the primary kill mechanism wasn't heat or radiation. It was the shockwave, a supersonic overpressure wall that struck a tank's vertical hull face, got underneath the ground clearance gap, and flipped the vehicle upside down in under a second. More armor made it worse. A heavier tank presented more surface area for the wave to act on. The only solution was a hull shape the shockwave couldn't lift. So they built one. To understand why the Object 279 looks the way it does, you need to understand what a nuclear shockwave actually is at tank operational range. The fireball is not the primary threat. At the distances where tactical nuclear weapons were expected to be used in a Cold War ground engagement several hundred meters to roughly 1 kilometer from the detonation point, the thermal pulse lasts milliseconds, and the radiation exposure, while lethal over time, doesn't immediately disable a vehicle. What arrives first, and with the most immediate mechanical consequence, is the shockwave. A wall of compressed air traveling at supersonic speed, carrying an overpressure that at close range can exceed several atmospheres above ambient. It doesn't burn, it pushes. And it pushes everything in its path simultaneously, from every direction the wavefront contacts. For a conventional tank, that creates a specific and catastrophic physics problem. A standard tank hull presents a tall, flat vertical face to an incoming shockwave. The wave strikes that face and transfers its overpressure load across the full frontal area of the vehicle. Simultaneously, the wave reaches the ground in front of the tank and travels along the surface, passing beneath the hull through the ground clearance gap, the space between the hull's underside and the terrain. The pressure above the hull and the pressure beneath it are not equal at the moment of shockwave arrival. The wave has struck the top and front surfaces before it has fully pressurized the underside. That pressure differential, acting across the full underside area of the hull, generates an upward force, aerodynamic lift. Applied instantaneously to a vehicle weighing 40 or 50 tons, the tank doesn't melt, it rotates. The shockwave gets under the hull, finds the lever arm created by the ground clearance gap, and flips the vehicle. In documented nuclear test exposures of armored vehicles at the Soviet Semipalatinsk test site, this was not a theoretical outcome. Tanks positioned at certain distances from detonation points were found inverted after the blast, mechanically intact, structurally undamaged, upside down and non-operational. Adding more armor does not solve this. It makes it worse. A heavier tank has greater mass, which resists the lift force to a degree, but a heavier tank also typically has a taller profile and greater frontal area, which means the shockwave has more surface to act upon. The lift force scales with the pressure differential and the area over which it acts. Mass works against lift, but area works for it. In the geometry of a conventional tank, area wins. The engineering conclusion was unambiguous. The shape of the hull was the variable that mattered, not its weight or its armor thickness. This was the design problem that the Object 279 was built to solve. Development began at the Kirov factory in Leningrad in 1957. The lead designer was Joseph Kotin, who had overseen Soviet heavy tank development since the Second World War. The design requirement was explicit. The vehicle had to remain operational after exposure to a tactical nuclear detonation at combat range. That requirement drove every visible feature of the machine. The hull cross-section is elliptical. Viewed from the front, the Object 279 presents a curved surface rather than a flat vertical face. An incoming shockwave striking a curved surface doesn't accumulate pressure at a single point. It is redirected outward and upward, dissipating across the curve rather than loading the full face simultaneously. The pressure differential between the hull's upper surface and its underside is reduced because the wave's energy is being deflected rather than absorbed. Less differential pressure means less lift. Less lift means the vehicle stays on the ground. The underside of the hull is not flat. It is shaped with a continuous curve from front to rear, sitting low to the ground with minimal clearance. This geometry directly attacks the mechanism that flips conventional tanks. The shockwave traveling along the ground surface encounters a hull underside that offers minimal gap to enter and a curved profile that redirects rather than captures the overpressure. The lever arm the shockwave needs to generate rotational force is dramatically reduced. At the distances and yield levels the Object 279 was designed for, the combination of elliptical cross-section and low curved underside kept the vehicle on the ground while everything around it was being displaced. The overall height of the vehicle is strikingly low for a heavy tank. At approximately 2.2 meters, it sits considerably closer to the ground than contemporary Soviet heavy tanks. That low profile is not a coincidence. Every centimeter of height reduction reduces the frontal area the shockwave can act upon and lowers the vehicle's center of gravity against rotational force. The shape that looks unconventional from any angle is the direct physical output of shockwave aerodynamics applied to vehicle geometry. 4 tracks are visible on the Object 279, 2 parallel assemblies on each side rather than the single track per side used on every conventional tank. Their purpose is not primarily traction. Post-nuclear terrain is not standard ground. A detonation at combat range produces cratered surface, thermally disturbed soil, displaced debris, and in some conditions partially liquefied ground material. A conventional 2-track layout exerts ground pressure concentrated across a narrower contact area. On post-blast terrain with degraded load-bearing capacity, that concentration causes the vehicle to sink and lose mobility at exactly the moment it needs to advance. 4 tracks distribute the Object 279's considerable weight, approximately 60 tons across a contact area, large enough to maintain mobility on terrain that would stop a conventionally tracked vehicle. Hull kept it on the ground. But a shockwave that can't flip the tank can still destroy every optical system, every seal, and every crew member inside through overpressure penetration alone. That required a second layer of engineering entirely. The shockwave problem had 2 components. The first was external, preventing the vehicle from being physically displaced. The hull geometry addressed that. The second was internal, preventing the overpressure wave from entering the crew compartment through gaps, apertures, and mechanical penetrations in the hull, and killing the crew through pressure trauma even while the vehicle remained upright. A nuclear detonation at close range produces an overpressure pulse that lasts only fractions of a second but is sufficient to cause fatal barotrauma. Internal organ damage from rapid pressure change to unprotected personnel. A tank crew inside a sealed steel box is not automatically protected. Every gap in the hull, every cable penetration, every vision port and hatch seal represents a potential pressure entry point. In a conventional tank, those gaps are accepted as a design trade-off. In the Object 279, they were eliminated. The hull was designed as a fully sealed pressure vessel. All penetrations through the hull plating for cables, controls, and mechanical linkages were sealed against overpressure ingress. The crew operated in a filtered internal atmosphere maintained at positive pressure relative to the outside. This positive pressure differential meant that any gap in the hull resulted in air flowing outward rather than contaminated or overpressured air flowing inward. Hatches were sealed with gaskets rated for the overpressure levels expected at the vehicle's operational range from a detonation. Vision systems were periscope mounted, with no direct apertures through the hull. The crew had no direct line of sight to the outside that wasn't mediated by a sealed optical path. This was not only a shockwave protection measure, it was simultaneously a nuclear, biological, and chemical protection system. A hull that excluded overpressure also excluded fallout particles, chemical agents, and biological contaminants. The Object 279's NBC protection standard was the most comprehensive fitted to any Soviet armored vehicle of its era, and it emerged directly from the nuclear survivability requirement rather than as a separate design addition. The 4-track system carried its own engineering complexity. Each of the 4-track assemblies was mounted on an independent suspension unit, allowing each assembly to respond to terrain variations without transferring load to the adjacent assembly. On post-blast terrain with highly irregular surface conditions, craters, debris fields, displaced large objects, independent suspension across 4 contact points maintained hull stability and crew effectiveness, where a rigid or semi-rigid four-track arrangement would have transmitted severe shock loads to the crew compartment. The suspension travel on each unit was substantial. Designed for the worst-case terrain the vehicle was expected to encounter after a nearby detonation. The Object 279 was not designed in isolation from empirical data. Soviet nuclear test programs at Semipalatinsk placed armored vehicles at measured distances from detonation points and examined the results. The flip mechanism was documented across multiple tests. Data from those trials established the overpressure levels and dynamic pressure loads the design needed to survive. Engineers had actual blast exposure data, not just theoretical models, to work against. The Object 279's design parameters were calibrated against measured outcomes from real nuclear detonations. What those tests also revealed was a failure mode the hull geometry couldn't fully address. Vehicles that survived the shockwave without flipping were sometimes immobilized by debris accumulation in their track assemblies, material displaced by the blast that packed into the running gear and prevented movement. The Object 279's four-track layout reduced this risk compared to a conventional two-track arrangement by distributing the track assemblies across a wider footprint, making simultaneous debris packing of all four assemblies less likely. It did not eliminate the risk. In extreme debris field conditions, track immobilization remained a documented vulnerability that no purely geometric solution could fully resolve. In 1960, Nikita Khrushchev canceled the Object 279 at the prototype stage. The cancellation was not a response to engineering failure, it was a response to a doctrine shift. Khrushchev's strategic posture moved Soviet nuclear capability toward intercontinental ballistic missiles as the primary deterrent, a strategic nuclear framework rather than a tactical one. In a strategic nuclear doctrine, the scenario the Object 279 was built for armor operating near tactical nuclear detonations on a conventional battlefield ceased to be a planning requirement. A tank that could survive a nearby nuclear blast had no operational context in a doctrine that assumed nuclear weapons would be used at intercontinental range against cities and infrastructure rather than at tactical range against ground forces. The Object 279 was formally rejected for production. One prototype was completed. It is preserved at the Kubinka Tank Museum outside Moscow, where it remains the only example in existence. The engineering it embodied was not discarded. The NBC sealing standards developed for the Object 279 positive internal pressure, sealed hull penetrations, filtered crew atmosphere were carried forward into the T-series tank family that became the backbone of Soviet armored forces through the remainder of the Cold War. Every Soviet tank from the T-64 onward incorporated NBC protection standards whose lineage traces directly to the work done for the Object 279. The shockwave geometry principles informed subsequent Soviet thinking on hull design for survivability, even as the specific nuclear survivability requirement that generated them was removed from the doctrine. The Object 279 was the most expensive answer to a question that stopped being asked. It was built for a war fought under rules that changed before the tank could enter service. The single prototype in Kubinka represents the terminal point of a specific Cold War logic that tactical nuclear warfare was survivable, that armor could operate near detonation points, and that a vehicle shaped correctly could drive through conditions that destroyed everything built before it. The shockwave couldn't flip it, the doctrine did.